For 100 years, we described stars to one another as giant balls of gas. We spoke of them as luminous clouds of hydrogen and helium, vast and airy spheres that held their shape through a delicate balance of heat and gravity. It was a comforting image of celestial lightness. That image is a lie, not a deliberate lie, but a necessary simplification. The universe builds with gas and destroys through pressure. In the wake of the most violent deaths in the cosmos, there are objects that defy every intuition we have about matter. These are the neutron stars. They take the mass of an entire sun and fold it down, pressing it tighter and tighter until the very atoms themselves collapse. The space between the nucleus and the electron vanishes. The structure of the atom is erased. What remains is a sphere with a diameter of only 20 kilometers, a celestial object that could fit within the boundaries of a small city, yet possesses more mass than our own sun. This is not gas. It is not plasma. It is something denser than any material we can create or even conceptualize on Earth. The scale of this transition is absolute. We move from the airy expanse of a living star to a solid frozen core of pure nuclear matter, a city-sized ghost that weighs more than 1,000,000 Earths. The sheer impossibility of this compression changes everything we thought we knew about the limits of physical existence. To grasp the scale, we must first discard our understanding of weight and volume as separate things. We are used to a universe where mass is spread out, where a mountain occupies miles of land and a planet spans thousands of kilometers. But here, the rules of geography are replaced by the rules of extreme compression. The object before us is not just small, it is an impossibility made manifest in the dark. The measurements tell a story of absolute concentration. We find that these stars typically hold between 1.4 and 2.1 times the mass of our own sun. Think of the sheer volume of that weight, the staggering amount of matter required to build a star like ours, and then imagine it all being forced into a space no wider than 20 kilometers across. It is as if we took every single grain of sand on every beach in the world, every drop of water in every ocean, and every mountain range on Earth, and crushed them until they occupied the size of a small pebble. The density here is not merely high, it is total. In our daily lives, we perceive solids as firm and unyielding, but compared to this, everything we touch is essentially a vacuum. The air around us is mostly empty space. Even the steel in our buildings or the diamond in a ring is composed of atoms that are almost entirely void, with tiny nuclei floating far apart from their electrons. But inside the boundary of a neutron star, there is no more room for emptiness. The mass of over one solar sun is packed so tightly that the distance between particles vanishes. The pressure becomes an irresistible force, driving protons and electrons together until they merge into neutrons. It is a process of cosmic erasure. The identity of the atom is lost, replaced by a sea of identical particles pressed shoulder to shoulder in a state of matter that cannot exist anywhere else in the observable universe. If you were to look at this object from a distance, it would appear as a tiny, blindingly bright sphere, a needlepoint of light against the oppressive black of the void. But its presence is felt long before it is seen. The gravitational pull is so intense that it warps the very geometry of space around it, bending the path of light and pulling at the fabric of time itself. It is a heavy ghost, an anchor of mass that refuses to be ignored by the cosmos. We are looking at a city-sized object that possesses the crushing power of a stellar giant. The ratio is absurd. A diameter of 20 kilometers holding two solar masses creates a gradient of gravity so steep that it defies our biological intuition. On Earth, gravity pulls us gently toward the center of a vast sphere. Here, the pull is an aggressive vertical plummet. This concentration of mass changes the nature of existence for anything that wanders too close. The boundary between a star and a black hole is defined by this very struggle. If the mass were any higher, if it pushed past that critical threshold of approximately 2.16 solar masses, no force in nature could stop the collapse. It would vanish from sight entirely, leaving only a hole in space-time. But for now, these stars hold their ground. They exist in a precarious balance, clinging to a physical form through a pressure so immense it is almost holy in its intensity. We are left with an object that is simultaneously tiny and overwhelming. It is a paradox of scale where the smallest visible structures in the galaxy carry the heaviest burdens of mass. The universe has taken the most common element in existence and folded it until it became something alien, something that behaves more like a single giant atomic nucleus than a star. It is a silent, heavy sentinel, drifting through the interstellar medium, carrying within its small frame the weight of an entire solar system's worth of matter. The sheer density creates a reality where the laws of physics are pushed to their absolute breaking point, forcing us to ask what happens when matter is forced into this state. Imagine the sheer silence of that space, a void where the very concept of distance begins to fail. We are accustomed to thinking of mass as something that occupies volume, something that spreads out across a landscape or fills a room. But here, the universe has performed a violent act of subtraction. It has stripped away every millimeter of wasted space, every gap between particles, until only the essence of matter remains. This is not merely density in the way we understand it on Earth. This is the collapse of the void itself. If you could somehow stand at the edge of this invisible boundary, you would feel a pull that does not just tug at your body, but reaches for the very architecture of your atoms. The gradient is so steep that the gravity at your feet would be meaningfully stronger than the gravity at your head, attempting to stretch you into a thin ribbon of existence. It is a gravitational slope so severe that it feels less like a force and more like a waterfall of space-time, dragging everything toward a center that refuses to yield. Within this city-sized sphere, the internal pressure creates a stillness that is terrifying in its absolute nature. There is no wind here, no movement, no vibration that isn't governed by the crushing weight of two solar masses pressing inward from every direction. The matter has been folded so many times that it has become a singular, monolithic entity. It behaves not as a collection of particles, but as one giant macroscopic nucleus, a single drop of nuclear fluid floating in the dark. The light that attempts to escape this region does not travel in straight lines. As photons climb out of this gravitational well, they are stretched and strained, their paths curving around the star like water flowing around a stone in a stream. This curvature creates a visual distortion where you could potentially see the back of the star while looking at its front. As the gravity bends the image of the far side around to meet your gaze, the object is so heavy that it cheats the geometry of the universe, turning the surrounding vacuum into a lens of impossible power. We often speak of the void of space as the great emptiness, but in the presence of such an object, the void feels thin and fragile. The neutron-star is the true solid, the only thing in the cosmos that possesses a tangible, uncompromising reality. Everything else, the gas clouds, the drifting asteroids, even the massive stars themselves, feels like ghosts by comparison, mere wisps of smoke floating around a diamond of infinite weight. It is a concentration of existence so extreme that it challenges our understanding of what it means to be physical. We are left contemplating a world where a few kilometers of space hold more truth and more power than an entire solar system of scattered planets. It is the ultimate expression of cosmic economy, where every single neutron is accounted for, packed into a sphere that serves as a permanent monument to the death of a giant star. Expectation, a smooth and fluid surface of liquid fire, much like the churning plasma we associate with our own sun. We tend to visualize stars as soft, glowing spheres where gas flows in endless currents, shifting and swirling under the influence of heat. But for a neutron star, this image is entirely wrong. Reality is far more rigid, far more alien. When you descend toward the surface of such an object, you are not approaching a cloud or a sea of plasma, but a fortress of metal. The pressure here has performed a feat of cosmic engineering that defies every intuition we have about materials. The outer layer of a neutron star is not gas, nor is it liquid. It is a solid crust composed primarily of iron nuclei, arranged in a perfect crystalline lattice. This is a world where the very atoms have been crushed into an orderly grid of unimaginable hardness. Imagine a diamond, then imagine that diamond's strength multiplied by billions until the material becomes so stiff that it makes any metal on Earth feel like wet clay. This crust is not a thin veneer. It has a solid thickness of approximately 1 kilometer. A single kilometer of crystalline iron compressed by gravity into a state where every gap between atoms has been erased. Right. If you could touch this surface, you would be touching the hardest substance in the known universe. There is no softness here, no give, only an absolute frozen rigidity that holds its shape against the most violent forces in the galaxy. The transition from the vacuum of space to this iron shell is instantaneous and brutal. One moment there is nothing but the cold void. The next you encounter a wall of matter so dense that it feels less like a physical object and more like a fundamental boundary of existence. The curvature of the star is so tight, the gravity so steep that any irregularity on the surface, even a mountain only a few millimeters high, would be an impossible feat of structural integrity. On Earth, mountains are built by tectonic shifts over millions of years. Here, the gravity would flatten a mountain in a heartbeat, yet the crust remains, locked in its crystalline grip. We often think of stars as the ultimate source of light and warmth, but this shell is a cold mask hiding a terrifying interior. Beneath that 1 kilometer of iron lies a strange ocean of neutrons, a superfluid where friction ceases to exist. The contrast is jarring. Above, a rigid frozen crust of metal. Below, a liquid heart of pure nuclear matter. This boundary represents the final line of defense against total collapse. It is the skin of a ghost, a thin layer of stability wrapped around a core that wants to shrink into nothingness. This crystalline shell does not just sit there in silence. Because it is so rigid, it can store energy like a coiled spring. When the star shifts or when its internal magnetic fields rearrange, this iron crust can crack. In any other environment, a crack is a sign of failure. Here, a starquake, a rupture in that 1 kilometer of solid iron, releases more energy in a fraction of a second than the sun emits in entire days. The surface snaps violently, sending shudders through the fabric of space. It is a place where geometry becomes oppressive. You are standing on a sphere 20 kilometers wide, but every single atom beneath your feet is screaming under the weight of 2 solar masses. The crust is the only thing preventing the star from becoming a singularity. It is a precarious shield, a thin layer of crystalline order maintaining a physical form in a region of space where physics usually demands chaos. The sheer scale of this rigidity creates a strange silence. There is no wind on a neutron star. There is no weather as we understand it. There are only the humming vibrations of a crystal lattice and the oppressive weight of an entire stellar remnant pressing down from above. The surface is so smooth yet so hard that it reflects the surrounding cosmos like a dark, distorted mirror of iron. But this structure, this 1 kilometer of unbreakable metal, cannot exist on its own. It does not stay solid because of temperature or chemistry alone. There is something deeper happening beneath the crust, a hidden war between gravity and the fundamental nature of matter itself. The iron shell is merely the visible result of an invisible force maintaining this impossible architecture from within. Imagine the silence of that surface. It is not a void, but a heavy, expectant stillness. If you could stand there for a single heartbeat, you would feel the universe pressing against you with a weight that defies description. Every fiber of your being would be stretched and pulled toward the center of the sphere with such intensity that the very concept of height or depth would vanish. You would not simply be on the star, you would become part of its geometry, flattened into a shimmering sheet of atoms only a few microns thick, fused forever into that crystalline iron lattice. This is the true nature of the crust, a graveyard of matter where everything has been forced into a state of absolute submission. The iron does not behave like the metal we find in our mines or use in our machines. Under this pressure, it becomes something more akin to a cosmic diamond, a structure so rigid that it resists the most powerful gravity in the known universe. It is a frozen sea of nuclei, locked in a grid where every single particle is pinned in place by the crushing weight of two suns. When you consider the sheer scale of this rigidity, you begin to understand why the surface remains so impossibly smooth. On Earth, we see mountains and valleys as signs of strength, but here any protrusion would be an act of defiance against physics. A pebble the size of a grain of sand would be an Everest in this world, yet even that is too much for the star to tolerate. The gravity acts like a cosmic iron, pressing every irregularity into a perfect, seamless curve. The result is a sphere so precise it makes our most advanced human engineering look like crude clay. But beneath this mirror-like finish, the tension is building. The crust is not merely a shell, it is a reservoir of stress. Because the star rotates with such dizzying speed, the iron lattice is constantly being twisted and pulled by internal magnetic forces that would tear an entire solar system apart. It is like a bowstring drawn tighter and tighter over thousands of years, holding back a flood of energy that has no way to escape. Then, in a moment of sudden, catastrophic failure, the crust gives way. The snap of a starquake is not a sound. Sound cannot travel through the vacuum, but it is a physical event that ripples through space-time itself. For a fraction of a second, the crystalline order collapses, and the stored energy erupts in a blinding flash of X-rays and gamma radiation. The surface does not just shake, it reconfigures. Entire continents of iron are shifted by centimeters, an adjustment that releases more power than a trillion nuclear bombs detonating at once. In those moments, the star screams into the void, sending a shockwave across the galaxy that tells us exactly how fragile this stability really is. It reminds us that this 1 kilometer of solid metal is not a fortress, but a thin membrane holding back an ocean of chaos. We are left to contemplate the strange duality of such a place. A surface as smooth as a polished jewel, yet possessing a violence that could erase a planet in an instant. It is a world where the most rigid material in existence is also the most volatile. The iron shell remains, shimmering and cold, acting as the final sentinel between the visible universe and the crushing mystery of the nuclear heart beneath it. Expectation, a perfect sphere of uniform density, rotating with mechanical precision, like a polished marble in the dark. Reality, an asymmetrical landscape where gravity bends light so severely that we can see more than half of the star at once. For years, the models assumed these remnants were simple, smooth balls of neutron matter, but when NASA deployed the NICER telescope, the data began to tell a different story. The neutron-star interior composition explorer was not looking for images in the traditional sense, but for the timing of X-ray pulses, measuring the subtle shifts in light as they curved around the object's horizon. When the team analyzed PSR J051, the results did not fit the old map. They found that the hot spots on the surface, Regions of intense thermal radiation where magnetic fields funnel energy were not neat poles at opposite ends of the star. Instead, they were shifted, clustered, and irregularly shaped. One hotspot was small and concentrated, while the other was a sprawling, chaotic smear of heat. This discovery meant the magnetic field of a neutron star is not a clean dipole, like a bar magnet, but a tangled web of flux that twists and knots beneath the iron crust. The geometry revealed by NICER suggests a world that is physically distorted by its own intensity. Because the gravity is so extreme, it creates a gravitational lens that wraps the image of the star around itself. As you drift closer to PSR J030+0451, you would see the backside of the star bleeding into the front, a visual hallucination caused by space-time curving in a tight circle. The surface is not just a place of heat and metal, but a mirror that reflects the impossible architecture of general relativity. The astronomers who processed these X-ray timings found themselves staring at data that defied their initial simulations. They had to refine their models multiple times, adjusting for the way the star's mass warps the path of every single photon leaving the surface. The realization was quiet but profound. These objects are not just dense, they are geometrically alien. The hotspots move and shift as the star spins, tracing erratic paths across a sky that is curved into a sphere. This irregular shape tells us that the interior is not a static sea of particles. There are currents flowing deep inside, movements of superfluid matter that push and pull against the crust from below. The asymmetry seen by NICER is a window into a hidden engine, a place where magnetic tension and quantum pressure fight for dominance over the star's physical form. We are no longer looking at a dead ember, but a complex pulsing machine of nuclear proportions. Every single photon captured by the telescope carried a piece of this puzzle, revealing that the surface is not a uniform wasteland. There are mountains of iron, only a few millimeters high, that possess more mass than at entire ranges on Earth. These tiny ripples in the crust create valleys and peaks of gravity so steep that they would shred any known material. The star is a study in contradictions, a city-sized object with the complexity of a galaxy, where a millimeter of height represents a mountain of impossible weight. As we observe these hot spots flickering across the surface of PSR J030+, we are seeing the thermal signature of an object that has forgotten how to be a star. It is now something else entirely, a condensed knot of existence where the laws of chemistry have been replaced by the laws of nuclear physics. The light does not just travel, it clings to the surface, orbiting the star in a desperate attempt to escape the pull. The data from NICER transforms our understanding of these objects from distant points of light into tangible, albeit terrifying, landscapes. We can now map the coordinates of the heat, trace the lines of the magnetic field, and feel the scale of the distortion. The universe does not build these remnants with symmetry in mind. It builds them through collapse, violence, and a relentless drive toward the smallest possible volume. And yet, this irregular surface is only the outer skin of the mystery. The hot spots and the warped geometry are merely symptoms of what is happening beneath that 1 kilometer of iron. There is a deeper pressure at play. Pick up a single teaspoon in your mind. Hold it between your finger and thumb, feeling its lightness, its mundane presence. Now, imagine that this small spoon is filled not with sugar or salt, but with a fragment of the matter we have been tracing, a tiny scoop of a neutron star's core. The weight of that single teaspoon would be approximately 1 billion tons. To hold it would be to hold something that defies every intuition we possess about what matter is. 1 billion tons of nuclear material compressed into a space smaller than a child's palm. If you were to place this spoonful on the surface of the Earth, it would not simply sit there. It would slice through the crust like a hot needle through silk, plummeting toward the center of our planet, because no material in our world is strong enough to support its impossible density. We often speak of mass and weight as if they are simple concepts, but here they become monsters. 1 billion tons is more than the combined weight of every human being currently living on Earth. Every man, woman, and child, every city, every mountain range we have ever climbed, all of that collective biological and geological presence weighed against a single teaspoon of this star. The scale does not just tilt, it breaks. This is what happens when the universe decides to remove the empty space from the heart of an atom. In our daily lives, atoms are mostly void. If an atom were the size of a great cathedral, the nucleus would be a small marble in the center, and the electrons would be tiny dust motes drifting far away in the rafters. Everything we touch, the air you breathe, the bed beneath you, your own skin, is composed almost entirely of nothingness. But inside the collapsed core of a massive star, that cathedral is crushed. The walls cave in, the empty space vanishes, and protons and electrons are forced together with such violence that they cease to be separate entities, merging into a sea of neutrons. This process removes the void, packing the mass of an entire sun into the volume of a small city. When we look at the number 1 billion tons per teaspoon, we are seeing the result of gravity winning its longest war. It is a state of matter where density has reached such an extreme that it begins to rewrite the rules of physical existence. The material is no longer chemical, it is nuclear. There are no molecules here, no bonds, no chemistry as we understand it. Only a crushing, singular pressure that keeps the star from collapsing further into a black hole. The sheer concentration of mass creates a tension in the vacuum itself. We can feel this weight even from across the void when we observe how these objects behave. The density is so absolute that the object ceases to be just a body moving through space and instead becomes a permanent distortion, a heavy anchor dragging at the very fabric of the universe. It is a silent, oppressive weight. 1 billion tons in a spoonful is not just a statistic. It is a revelation of how far the cosmos can push matter before it breaks. We are drifting now toward the edge of this density, where the mass no longer just sits within the star, but begins to warp everything around it. The gravity here does not just pull on objects. It pulls on light itself, bending the path of photons and curving the geometry of the void into a deep, inescapable well. This is how such impossible density affects the fabric of space. The sensation of this weight is something the human mind was never designed to hold. We are creatures of a world where a mountain feels eternal and an ocean seems bottomless. But those are illusions of scale born from our own fragility. To imagine 1 billion tons in a small spoonful is to step outside the boundary of biological intuition and enter a realm of pure, oppressive geometry. It is not just that the matter is heavy, it is that the space it occupies has been forced to surrender. If you could reach out and touch this substance, your hand would not feel a surface in any way we recognize as solid. You are used to the resistance of atoms pushing back against other atoms, the electromagnetic repulsion that allows your feet to stand on the floor without sinking through it. But here, that repulsion has been utterly defeated. The force of gravity is so absolute that it has crushed the very electrons into the protons, erasing the distance between them. You would be touching a material that is not made of elements, but of concentrated existence itself. Think for a moment about the silence of such an object. In our world, weight creates sound, a falling stone crashes, a shifting glacier groans, but this density exists in a state of terrifying equilibrium. The billion tons do not vibrate or shift. They are locked in a frozen nuclear embrace, held together by a pressure that makes the depths of our own oceans feel like a thin mist. It is a stillness born from total victory. the point where gravity has finally won its war against every other force in nature. This concentration of mass creates a strange, invisible tension that radiates outward into the void. Even if you were to float miles away from this spoonful of matter, you would feel the fabric of space-time stretching toward it, like a heavy sphere resting on a sheet of taut silk. The vacuum is no longer empty. It is curved. It is warped. Every photon of light passing near this tiny point of mass is forced to bend and diverted from its straight path by a gravity that refuses to let anything go unnoticed. We spend our lives believing that the world around us is solid, that the walls of our homes and the ground beneath our feet are the definition of substance. But compared to the heart of a neutron star, everything we have ever known is a ghost. Our cities, our planets, and even our sun are mostly empty space, fragile bubbles of gas and dust drifting in a vacuum. We live in the gaps. We exist in the void between particles, but here, in this single teaspoon, the void has been exiled. The universe has decided to see what happens when it removes every single breath of room between its components. The result is a density that defies description, a physical paradox where the small becomes the heaviest thing in the cosmos. It is a reminder that the laws of physics do not care for our comfort or our intuition. They only care for the balance of power, and in the presence of such mass, the power belongs entirely to the crush. As we drift further into this realization, the weight begins to feel less like a number and more like a presence. 1 billion tons is not just a measurement, it is an anchor. It is a point of absolute certainty in a universe of drifting clouds. The sheer intensity of this mass creates a gravitational well so steep that time itself begins to behave differently near its edge, slowing down as if the weight were pulling on the seconds and minutes, dragging them into its own suffocating rhythm. It is here, at the limit of what matter can endure, that we find the true nature of cosmic violence. Not in an explosion or a crash, but in the quiet, relentless pressure of 1 billion tons compressed into a space smaller than a child's palm. It is the ultimate expression of gravity's will, a singular, heavy truth that transforms the very definition of what it means to exist as a physical object. The silence of deep space is rarely absolute, but for a long time we believed it was mostly empty of rhythm. We expected the remnants of dead stars to be quiet, cold spheres drifting in the dark, invisible ghosts that left no trace of their former glory. But in 1968, a team led by Jocelyn Bell Burnell and Anthony Hewish encountered something that defied every existing map of the radio sky. They were scanning the heavens with a massive array of antennas when they found a signal that did not behave like any star or planet known to science. It was a pulse, a sharp rhythmic beat appearing every 1.33 seconds over and over with a precision that felt artificial. The team who first saw these data prints went very quiet. They stared at the charts of radio noise and found something so unnervingly regular that they didn't believe their own equipment. In those early days, the pulse was so exact, so clock-like, that it earned a temporary whispered nickname among the researchers, LGM-1, Little Green Men. The suspicion was not born of fantasy, but of sheer disbelief. No natural object in the universe had ever shown such timing. To the astronomers of 1968, this looked less like a star and more like a beacon sent from another civilization, a deliberate signal flashing across the void to announce its presence. They checked the calibrations 3 times. They searched for interference from local radar or terrestrial noise, but the source remained fixed in the distant stars. It was as if the universe had suddenly started ticking. The precision was absolute, far beyond anything a normal star could produce. A typical star is a chaotic ball of plasma swirling with turbulence and unpredictable flares. But this object was different. It was not pulsing because it was breathing or vibrating. It was flashing like a lighthouse on a coast of eternal night. What the team had actually discovered were pulsars. These are neutron stars that have evolved into the most accurate clocks in existence. The disbelief felt by the observers came from the gap between what they knew about matter and what they were seeing in the data. How could something so massive, yet so small, spin with such unwavering regularity? The answer lay not in alien technology, but in the terrifying efficiency of a collapsed core. When we look at these pulses now, we are hearing the scream of a star that refused to disappear entirely. When the massive star died and its core collapsed into a city-sized sphere of neutrons, it shrank and began to spin. This is the law of conservation of angular momentum, the same principle that makes a figure skater spin faster as they pull their arms inward. But while a skater pulls in their limbs by a few feet, a dying star pulls its entire mass from millions of kilometers down to a diameter of only 20 kilometers. The result is a rotational velocity that defies human intuition. The object becomes a spinning top of impossible density, rotating hundreds or even thousands of times per second. As it spins, it emits two narrow beams of intense electromagnetic radiation from its magnetic poles. These beams sweep across the vacuum of space in a wide arc. If Earth happens to lie in the path of that beam, we see a flash of light every time the star completes a rotation. We are not seeing the star itself, but a sliver of its energy brushing past our telescopes once per turn. What makes this so haunting is the scale of the precision. The timing of these pulses is so stable that they can be used to detect gravitational waves or measure the drift of continents on Earth. It is a mechanical perfection born from extreme violence. The very pressure that crushed protons and electrons into neutrons also locked the star into this rigid, spinning state. The observers in 1968 had stumbled upon a skew of objects that did not fit into the old maps of astronomy. They found that these pulsars were not lone anomalies, but a widespread population of stellar corpses, each one marking the grave of a giant. The shock of the discovery shifted our understanding of the cosmos from a place of slow, drifting gases to a place where matter can be forged into something as hard and precise as a diamond clock. The signal that once looked like an alien greeting was actually the signature of gravity's ultimate victory. It was the sound of mass so concentrated that it had warped its own identity, turning from a source of light into a cosmic metronome. We began to realize that these objects were not just remnants, but active engines, processing energy in ways that no laboratory on Earth could ever replicate. The pulse is the only way we can truly see them. Without those beams of radiation, these stars would remain hidden in the dark, their presence known only by the way they bend the light of distant galaxies behind them. But as long as they spin, they announce themselves to the void, sending a rhythmic reminder of the violence that created them. And yet, the pulse is only the beginning of the story. The beam itself is just a symptom of an even more powerful force hidden within the star's rotation, a mechanism that drives these cosmic lighthouses across the silence of space. When we first began to map these objects, it was natural to see them as static spheres of impossible density, frozen monuments left behind by a dying star. We saw them as silent anchors in the dark, their only activity being the steady rhythmic beam of radiation sweeping across our telescopes like a lighthouse on a distant shore. But the rhythm itself held a secret that shifted everything we thought we knew about stellar remnants. The pulse was not just a signal, it was a measurement of speed. The conservation of angular momentum dictates that when something massive shrinks, it must spin faster to compensate for its lost size. This is the same principle that causes a figure skater to whirl with sudden intensity as they pull their arms close to their chest. Now, imagine this process applied to an entire star. A giant that once spanned millions of kilometers has been crushed down to a diameter of only 20 kilometers. All that rotational energy, all that momentum from its former life, is now concentrated into a city-sized sphere. The result is a rotation speed that defies our terrestrial intuition. In some cases, the surface of these stars rotates at nearly 25% of the speed of light. Pause for a moment and try to visualize what that means. Light travels at 300,000 kilometers every single second. To move at 1/4 of that speed is to traverse the entire circumference of the star in a fraction of a heartbeat. The surface of the neutron star is not merely spinning, it is screaming through the vacuum, moving so fast that the very fabric of space-time around it begins to drag and twist. This velocity transforms the star from a simple object into a high-energy engine. At 25% of the speed of light, the centrifugal forces are immense, fighting against the crushing grip of gravity and a violent tug-of-war that determines the star's very shape. If they spun any faster, the star would fly apart, shedding its outer layers into the void. They exist on the absolute edge of physical stability, balanced between total collapse and total disintegration. When astronomers first calculated these speeds, there was a period of profound silence in the research rooms. The numbers felt wrong. It seemed impossible for a solid object to maintain such velocity without shattering, but the data from the pulsars remained stubborn. Every single pulse arrived with a precision that could only be explained by this terrifying rotation. They weren't looking at stars as we understand them. They were looking at the most precise mechanical objects in the known universe, spinning with a fury that makes our fastest turbines look like they are standing still. This rotation is what powers the beam of radiation we detect on Earth. The magnetic field of the star is locked into its rotation, and as it spins, it flings out beams of energy from its poles. Because the star rotates so rapidly, these beams sweep across space with a frequency that can reach hundreds of times per second. We are not seeing a steady light. We are seeing the strobe effect of a cosmic machine working at a speed that borders on the edge of physics. The sheer kinetic energy involved is staggering. A neutron star spinning at this rate possesses more rotational energy than some entire galaxies possess in their collective movement. It is a reservoir of power so vast that it can influence the environment around it for light years, sculpting the interstellar medium and ionizing the gas in its vicinity. We often think of the vacuum of space as empty, but around a rapidly spinning neutron star, the vacuum becomes an active participant. The interaction between the rotating magnetic field and the surrounding plasma creates a storm of particles accelerated to relativistic speeds. It is a zone where the laws of classical physics break down and are replaced by the strange, distorted rules of general relativity. We began to see that these objects were not just corpses. They were survivors of a process that stripped away everything unnecessary: the outer layers of hydrogen, the helium shells, the burning core, leaving behind only the most essential, hardest, and fastest part of the star. The violence of the supernova did not just destroy, it refined. It took a slow-moving giant and forged it into a relativistic spinning top. As we watch these pulses from our distant vantage point, we are witnessing the aftermath of a cosmic collapse that has reached its logical conclusion. The matter has been squeezed so tightly that it can no longer be described as gas or liquid, but as a strange, degenerate fluid that supports this incredible rotation without breaking. It is a state of existence where mass and velocity merge into a single, overwhelming force. And yet, some rotate with a different kind of violence. The speed of this rotation is not merely a number in a ledger, but a physical force that reshapes the very geometry of space and time around the star. Imagine the surface as it moves, a blur of matter so dense it defies description, whipping around its axis with such intensity that the centrifugal force fights against the crushing grip of gravity. This creates a subtle, invisible tension, a stretching of the sphere into an oblate spheroid, where the equator bulges slightly under the pressure of its own velocity. It is a cosmic struggle occurring in total silence, a battle between the desire to collapse inward and the momentum that threatens to fling everything outward into the dark. If you could stand at the edge of this rotation, though your body would be rendered into a thin film of atoms long before you arrived, you would perceive a world where distance is distorted. The sheer speed ensures that the star's magnetic field is not just a static aura, but a coiled spring of energy, winding tighter and tighter with every millisecond. This creates a vacuum that is no longer empty, but charged with an electric intensity that could strip the electrons from any atom that dared to drift too close. The space surrounding the star becomes a shimmering veil of relativistic plasma, dancing in synchronization with the spin of the core. This mechanical precision serves as a haunting reminder of what was lost during the supernova. The original star was a sprawling giant, a slow-burning furnace of hydrogen and helium that spanned millions of kilometers. Now all that grandeur has been distilled into this tiny, frantic engine. It is as if the universe took a symphony and compressed it into a single piercing note, held forever at a frequency that borders on the impossible. The rotation is the ghost of the original star's angular momentum, preserved through the collapse, accelerated by the same logic that makes a spinning ice skater move faster as they pull their arms inward. The energy stored in this motion is so immense that it behaves like a battery for the cosmos. For eons, the star slowly leaks this rotational energy into the surrounding void, powering the lighthouse beams of the pulsar and heating the interstellar dust to glowing temperatures. We are witnessing a slow decay of motion on a scale we cannot truly fathom, a gradual winding down of a clock that was set in motion by the death of a sun. Every pulse we detect is a tiny fraction of that momentum being surrendered to the vacuum, a rhythmic heartbeat echoing across the light years. The stability of this state is a miracle of quantum mechanics. The neutrons are packed so tightly they form a superfluid, a liquid with zero viscosity that flows without friction. This allows the interior of the star to rotate independently of its crust, creating internal vortices and glitches, sudden jumps in rotation speed that signal a shifting of the inner gears. These events are like cosmic earthquakes, ripples of energy that travel through the degenerate matter, reminding us that even an object this dense is subject to the laws of fluid dynamics, albeit on a scale where gravity has rewritten every rule we know. In this environment, time and space are no longer separate entities, but are woven together by the star's rotation. The frame-dragging effect begins to emerge, where the spinning mass actually drags the fabric of space-time along with it, twisting the void into a spiral. A particle falling toward the surface would not move in a straight line, but would be forced into a swirling descent caught in the wake of the star's terrifying velocity. It is a region of space that has been physically warped by motion, turning the vacuum into a whirlpool of gravity and light. This rotation transforms the neutron star from a simple remnant into an active sculptor of its galaxy. The winds generated by this spinning magnetic engine push against the surrounding gas, carving out vast bubbles of emptiness in the interstellar medium, creating voids that stretch for parsecs. It is a silent architecture of absence, where the fury of a city-sized object dictates the structure of the space around it for trillions of miles. And yet, some rotate with a different kind of violence. Close your eyes and feel the weight of your own body against the bed, the simple, familiar pull of Earth that keeps you grounded in a world of soft edges and slow movements. Now, let that sensation shift, sliding away from the safety of our home and drifting toward the surface of a neutron star. As you approach this city-sized sphere, the gravity does not just pull at you, it claims you with an absolute, terrifying authority. There is no gradual descent here, only a sudden and total surrender to a force that operates on a scale beyond biological comprehension. The surface gravity of a neutron star is 10 to the 11th power times greater than that of the Earth. It is not merely a stronger version of what we feel every day. It is a fundamental rewriting of how matter interacts with space. At this magnitude, the very concept of height becomes meaningless. If you were to drift toward the surface, you would not land so much as you would be integrated into the star itself. The pull is so violent that any object, no matter its composition or strength, would be instantly flattened. Mountain, a skyscraper, or human being would be crushed in a fraction of a second, compressed until it became a layer only one atom thick. You are no longer a three-dimensional entity. You are a shimmering two-dimensional film of particles smeared across the crystalline crust like a thin coat of paint on a sphere of impossible density. Every molecule is stripped of its structure, every chemical bond snapped by the sheer weight of the space above it. The gravity here does not just bend light or warp time. It dictates the exact geometry of existence, forcing everything into a state of absolute flatness. What does it mean to exist in a place where the vertical dimension is erased? On Earth, we measure distance in kilometers and meters, but on the surface of a neutron star, the only meaningful measurement is the thickness of a single nucleus. The pressure is so immense that there is no room for gaps, no space for air, no void between atoms. You are pressed into the iron crust with such force that you become part of the lattice. Your own atoms forced to merge and align with the degenerate matter beneath. This is the true nature of cosmic violence. Not a loud explosion or a crashing wave, but a silent, inevitable compression. It is the gravity of an entire sun condensed into the size of a small city, pulling from every direction with a hunger that cannot be satiated. The light itself struggles to escape this grip, curving in tight arcs around the horizon, allowing an observer to see more than half of the star at once because the gravity bends the image of the far side back toward the eye. We often speak of gravity as a gentle guide, the force that keeps our moon in orbit and our feet on the soil, but here it is a sculptor of extremes. It takes the chaotic debris of a dead star and polishes it into a sphere of perfect, lethal precision. The surface is not just hard. It is the hardest material known to exist in the observable universe, forged by a pressure that makes the center of the Earth feel like a cloud of steam. If you could survive for one heartbeat on this surface, you would perceive the universe as a distorted, swirling kaleidoscope. The stars above would be shifted in color and position, dragged downward by the gravitational well. The horizon would seem to curve upward, wrapping around you in a sphere of oppressive mass. You are standing at the bottom of the deepest hole in the fabric of space-time, a place where the laws of physics have been pushed to their absolute breaking point. The silence here is total, yet it is a silence filled with tension. Every millimeter of that one-atom-thick layer is screaming under the weight of two solar masses pressing down from above. It is a state of equilibrium, maintained by forces we can only describe through mathematics. The delicate balance between the crushing urge to collapse further and the desperate resistance of neutrons pushed together until they can no longer shrink. As you drift away from that flattened horizon, leaving behind the image of your own atom-thin shadow etched into the iron crust, the scale of this power begins to settle in. It is not just a quirk of astrophysics or a mathematical curiosity. This gravity is the signature of a transformation so profound that it erased the identity of a giant star and replaced it with something far more concentrated and dangerous. The sheer magnitude of 10 to the 11th times Earth's gravity suggests a history of unimaginable pressure, a sequence of events that took a sprawling cloud of gas and forced it into this singular crushing point. To understand how such a small object can exert such an overwhelming influence on the universe, we have to look back at the moment the balance failed. We must trace the path from a living star to a dead core, searching for the origin of such crushing power. To find the origin of this crushing power, we must travel backward through time, moving away from the cold, silent remnant and returning to a state of blinding, chaotic heat. We are looking for the ghost of a giant, a star that once dominated its neighborhood with a brilliance that dimmed everything around it. Not every star is capable of this transformation. The small ones, like our own sun, will fade quietly into white dwarfs, drifting as embers in the dark. But there is a specific class of celestial giants, stars born with a mass between 8 and 25 times that of our sun, that are destined for a far more violent conclusion. For millions of years, these stars exist in a state of desperate tension. They are massive enough to fuse not just hydrogen into helium, but to push deeper, forging heavier and heavier elements in their burning hearts. Carbon becomes neon, neon becomes oxygen, oxygen becomes silicon. Each stage happens faster than the last, as the star consumes its own fuel in a frantic attempt to hold back the weight of its own outer layers. The core becomes an onion of nuclear fire, with each layer pressing down on the one below it, creating temperatures and pressures that defy our earthly intuition. Then comes the iron. Iron is the dead end of stellar fusion. Unlike the elements before it, fusing iron does not release energy. It consumes it. The moment the core becomes dominated by iron, the engine stops. The outward pressure that has held the star aloft for eons simply vanishes in an instant. In a fraction of a second, the balance that defined the star's entire existence is shattered. Gravity, which had been waiting for this exact moment, finally wins. The collapse is not a slow descent. It is a free fall of unimaginable proportions. The outer layers of the star, millions of kilometers of plasma, suddenly find themselves falling inward at nearly a quarter of the speed of light. They are rushing toward a core that is shrinking from the size of Earth to the size of a city in milliseconds. As this matter slams into the ultra-dense core, it creates a shockwave of such intensity that it rips the star apart from the inside out. This is the supernova, a flash of light so powerful it can, briefly outshine an entire galaxy of hundreds of billions of stars. It is a scream of energy that flings heavy elements across the void, seeding the clouds of gas and dust with the raw materials for future worlds. But while the outer shell is being blasted into space, something far more strange is happening at the center. The collapse continues long after the explosion has begun. The pressure becomes so absolute that it begins to overwrite the laws of chemistry. Protons and electrons, the building blocks of every atom we have ever touched, are crushed together with such force that they cease to exist as separate entities. They merge, forced by the sheer weight of the falling star, into a sea of neutrons. The core does not just shrink, it transforms into a state of matter that cannot exist anywhere else in the observable universe. This is where the neutron-star is born. The collapse only stops when the neutrons themselves are packed so tightly that they refuse to be compressed any further, creating a wall of resistance known as neutron degeneracy pressure. Imagine the violence of that transition. A sphere of plasma larger than our solar system's inner orbits is condensed into a ball 20 kilometers wide. All that mass, all that gravity, now concentrated into a single city-sized point. The energy released in this process is so vast it ripples through the fabric of space-time itself, sending tremors across the cosmos that we can detect billions of light years away. The supernova is the fire that cleanses the star's identity, stripping away everything except the most concentrated essence of its being. It is a moment of total destruction that creates the most durable object in existence. The shock wave carries away the debris, leaving behind a naked, spinning core of pure neutron matter, glowing with a heat that would vaporize any planet in an instant. As the echoes of the explosion fade and the expanding cloud of gas drifts further into the dark, the newborn star begins to settle. It is no longer a sun, it is something else entirely. It is a relic of extreme physics, a diamond-hard sphere of neutrons that will spend the next few billion years cooling in the silence of the void. The fire has gone out, and the chaos has subsided into a terrifying rhythmic stability. The violence of the supernova was merely the birth pangs of this object. Now it remains as its silent sentinel, waiting to be discovered by the light of its own radiation or the pull of its impossible gravity. What remains after the fire fades is not just a dead star, but a laboratory where nature tests the absolute limits of matter. There was a quiet assumption in the early days of astrophysics that these objects were merely cosmic fossils, cold and static monuments to a dead star's former glory. The idea was simple. Once the supernova fire burned out, the remaining core would simply sit in the dark, slowly fading into an eternal frozen sleep. It felt logical. In the vast emptiness of space, where temperatures hover just above absolute zero, a small city-sized sphere should have become a dormant relic almost immediately. But the universe does not operate on such simple logic. When we looked closer, we found that neutron stars are far from static. They are some of the most active and energetic entities in existence, beginning their lives not in cold silence, but in a state of blinding, impossible heat. In those first moments after the collapse, the surface temperature of a newborn neutron star reaches millions of Kelvin. Try to hold that number in your mind for a second. We are not talking about the warmth of a summer day or even the searing heat of a blast furnace on Earth. This is a temperature so extreme that the very concept of light changes. At millions of degrees, the surface does not just glow. It screams in X-rays, pouring out radiation that would strip the electrons from every atom in a nearby planetary system. The star is a white-blue needle of energy piercing through the void, radiating a heat born from the sheer violence of its own compression. This thermal energy is not just a remnant of the explosion. It is a reservoir of power that keeps the star evolving for thousands of years. As these millions of degrees slowly bleed away into the vacuum, the star undergoes a slow, grinding transformation. The liquid interior begins to crystallize. The crust we spoke of earlier does not start as a rigid shell, but hardens over time, locking the star's geometry into place as it cools. And yet, even as they cool, these stars are never truly still. They possess a hidden internal life, driven by the tension between their cooling cores and their spinning surfaces. Some experience starquakes, where the crystalline crust reaches its breaking point and snaps under the pressure of the star's own gravity. A shift of only a few millimeters on the surface of a neutron star releases more energy than a billion nuclear bombs, sending shock waves through the stellar body and altering the timing of their radio pulses. The scientific community found this unsettling. The people who first mapped these objects expected a predictable decay, a linear slide into darkness. Instead, they found an object that behaves like a living thing, pulsing, snapping, and radiating with a ferocity that defies the surrounding cold. It is a contradiction of scale, a tiny sphere that commands an entire sector of space through sheer thermal and gravitational dominance. We began to realize that we were not looking at dead embers. We were looking at engines. These stars are converting their rotational energy into radiation, turning their own momentum into beams of light that sweep across the galaxies like cosmic searchlights. Every pulse is a heartbeat, every X-ray flare, a gasp of remaining heat from a birth that happened millions of years ago. The cooling process itself takes an unimaginable amount of time. While the surface drops from millions of Kelvin over millennia, the core remains a dense, hot mystery for much longer, insulated by the most efficient shielding in the universe, a sea of degenerate neutrons. This ensures that even the oldest neutron stars, those billions of years old, still carry a ghost of that original violence within them. As we drift further away from the heat of these dying suns, we start to notice something strange about the way they communicate with us. They do not just send light, they send rhythms. These rhythms are so precise that they rival the most accurate atomic clocks ever built by human hands. But as our instruments became more sensitive, we realized that the radio beams were only part of the story. The universe was trying to tell us something through a different medium entirely, one that does not rely on light or radiation, but on the trembling of space itself. It is a new way to hear the universe. For a long time, we viewed these city-sized remnants as solitary ghosts, drifting in the silence of the void, forever isolated by the distance between them. We assumed that once a star collapsed into this state, its primary journey was one of slow cooling and eventual invisibility. But the universe rarely permits such simple endings. In many parts of the cosmos, neutron stars are not alone. They are born in pairs, locked in a gravitational dance that lasts for millions of years. They orbit one another with an intensity that defies our intuition. Two spheres of impossible density spiraling inward, drawing closer and closer as they bleed energy into the vacuum of space. As these binary systems tighten their circle, they do something that light cannot describe. They begin to stretch the very fabric of reality. Every time these massive objects accelerate around each other, they send out ripples, shudders in the geometry of space-time itself. These are gravitational waves, invisible tremors that travel across the universe at the speed of light, carrying the signature of a collision long before it actually happens. For years, we could only theorize about this phenomenon, imagining the violent end of such a pairing as a mathematical possibility. We had the equations, but we lacked the ears to hear them. That changed in 2017 when the LIGO and Virgo detectors captured an event that would redefine our understanding of cosmic violence. It was designated GW-70817. For seconds, two neutron stars collided with such force that they shook the entire observable universe. The signal was a chirp, a rising frequency of gravitational waves that told us exactly how fast these objects were spinning and how quickly they were falling into one another. When the merger finally happened, it was not a quiet disappearance. It was an explosion of energy so profound that it produced light across every single part of the electromagnetic spectrum. From radio waves to gamma rays, the team behind the detection experienced a moment of collective shock. They had seen black hole mergers before, but this was different. A black hole merger is a dark event. It consumes everything and leaves nothing behind. But GW-708 left a residue. It created a kilonova, a radioactive fireball that glowed with the heat of billions of suns for days on end. Astronomers who had spent their lives studying the quiet pulses of isolated stars suddenly found themselves staring at a chaotic, blinding forge. They realized they were witnessing something that happens only once in 1,000 years in any given galaxy, the birth of new matter from the wreckage of old stars. What is actually happening during such a merger? As the two stars touch, the tidal forces are so extreme that they literally rip each other apart before they even merge into one body. Imagine the surface gravity we discussed, that crushing power 10 billion times stronger than our own world, now pulling from two opposite directions at once. The crusts of these stars shatter. Matter is flung out into space at a fraction of the speed of light, creating a spray of neutron-rich debris that expands outward like a cosmic shockwave. In those final milliseconds, the pressure and temperature reach levels that cannot be replicated in any laboratory on Earth. Protons and electrons are forced together with such violence that they create an environment where the laws of conventional chemistry cease to function. This is not just a collision of matter, it is a transformation of identity. The extreme density provides the perfect conditions for the R process, a rapid capture of neutrons that allows atoms to grow larger than anything and produced in a standard supernova. We often think of the universe as a place where things break down and fade away, but GW 670817 proved that the most violent deaths are also the most productive births. The collision did not just create a new, more massive object, it seeded the surrounding space with heavy elements. It turned the void into a workshop. As we drift through the aftermath of such an event, we can almost feel the residue of that energy lingering in the dark. We see the glow of the kilonova fading slowly, leaving behind a ghost of the collision and perhaps a new black hole where two stars once lived. But the most enduring legacy of this merger is not the light or the gravitational waves. It is the physical matter left behind, the heavy atoms that were forged in those final moments of pressure and heat. The universe does not just move things around, it changes what they are. The collision of two neutron stars is the ultimate act of cosmic alchemy, turning the simplest particles into the most precious materials in existence. And as we look at the debris of GW 1787, we realize that this violence was necessary for the world we know to exist. The alchemy born from this collision, the silence that follows such a collision, is not a true silence, but a vibration that ripples through the very fabric of existence. As we drift further into the wake of GW 1707, imagine the distortion of space itself as a physical thing, like a heavy stone dropped into a still pond, sending waves outward across billions of light years. These gravitational waves are the only honest record of the event, carrying the signature of two city-sized worlds spiraling inward at nearly the speed of light. They do not travel through space. They are the stretching and squeezing of space itself, a rhythmic shudder that tells us exactly how much mass was involved and how violently it was rearranged. Consider the sensory impossibility of those final moments. In the void of deep space, there is no air to carry sound, yet the collision produces a roar in the language of gravity. It is a crescendo of energy so profound that it bends the path of light passing nearby, creating a shimmering, distorted lens around the wreckage. If you were standing at a safe distance, you would see the stars behind the merger warp and dance, pulled by the sudden shift in mass as two distinct objects became one singular, screaming point of density. The debris cloud, expanding from the center, is not merely gas or dust. It is a spray of nuclear fire, an ocean of neutrons searching for stability. This material is so hot and so dense that it behaves like a fluid made of pure energy. As it expands into the cold vacuum, it begins to cool, but only slowly. In this cooling process, the chaos settles into order. The simplest particles begin to cling together, building atoms larger and heavier than anything the quiet life of a normal star could ever manage. We can almost feel the oppressive weight of that environment, the way gravity attempts to pull every single stray particle back into the center, while the explosive energy of the kilonova fights to push everything away. It is a cosmic tug-of-war played out on a scale where an entire solar system would be a mere footnote. The resulting glow is not just light, it is the radioactive decay of newly forged elements, a shimmering curtain of gold and platinum being woven into the void. This process happens in a blink, yet its effects last for eons. The heavy atoms created in this violence do not stay where they were born. They are carried by the shock wave, drifting through the interstellar medium like seeds scattered by a storm. They travel across the emptiness, eventually finding their way into new clouds of gas and dust, which will one day collapse to form new stars, new planets, and perhaps eventually the chemistry of life itself. The violence is not an end, but a redistribution. The universe takes the most extreme state of matter, the crushed, degenerated heart of a dead star, and unlocks it, releasing its contents back into the cosmos in a transformed state. It is as if the universe decided that the density of a neutron star was too great to be kept in one place, and so it used the collision to break the lock, spilling the treasures of the nuclear forge across the galaxy. As we linger in this aftermath, we realize that the void is never truly empty. It is filled with these ghosts, the lingering radiation of mergers from millions of years ago, the heavy metals drifting through the dark, and the silent ripples of gravitational waves still traveling toward distant horizons. Every piece of gold ever mined from the Earth is a relic of this specific, terrifying beauty. Each atom is a frozen scream from a collision that happened before our sun was even born, a physical memory of two stars that loved each other with such gravity that they destroyed themselves to create something new. There is a quiet moment that happens in the offices of astrophysicists, a moment where the mathematics on a screen transforms into something tangible. It happens when a researcher looks down at the gold band on their finger or the platinum setting of a wedding ring and realizes they are not looking at jewelry but at the debris of a cosmic catastrophe. For a long time, there was a gap in our understanding of where these heavy elements came from. We knew that stars forged carbon and oxygen, and we knew that supernovas could create some heavier atoms, but the math for gold and platinum never quite added up. The universe seemed to have more of these precious metals than the standard deaths of single stars could explain. Then came the data from JW 70817, when the gravitational wave detectors felt the shudder of two neutron stars spiraling into one another. It was not just a victory for physics. It was a revelation about our own chemistry. The team analyzing the light from that merger saw something they had only ever seen in theoretical models. They witnessed the R process in action, the rapid capture of neutrons. In the chaotic wake of the collision, where neutron-rich matter is flung into the void at a fraction of the speed of light, the environment becomes an atomic forge. Neutrons are slammed into seed nuclei so quickly that they bypass the usual limits of stability, building larger and heavier atoms in a frantic burst of synthesis. This is how gold is born. This is where platinum comes from. These elements require a density and a flux of neutrons that simply do not exist anywhere else in the cosmos. A single star cannot provide enough of this specific violence to seed a galaxy with gold. It takes the collision of two city-sized remnants, each weighing more than our sun, crashing together with such force that they tear the very fabric of space-time. The gold you might hold in your hand right now did not drift slowly through the void. It was screamed into existence during a merger that would have blinded any observer for light years around. There is a profound irony in this. We treat these metals as symbols of luxury and permanence, objects of desire that we keep in vaults or wear as heirlooms, but their origin is the most unstable event imaginable. Every gram of gold on Earth is a fragment of a dead star's ghost, a piece of shrapnel from a collision that happened millions, perhaps billions of years ago. We are wearing the scars of the universe's most violent transformations. When astronomers first confirmed this link, it changed the way they looked at the night sky. The void was no longer just a graveyard of dead stars. It became a warehouse of raw materials. They realized that every time two neutron stars merge, they are not just destroying themselves, they are enriching the universe. They are scattering the building blocks for future planets, and perhaps, eventually, the jewelry of civilizations yet to be born. The R process is the signature of this violence, a chemical fingerprint left behind in the crust of our planet that points directly back to these colliding spheres of degenerate matter. If you look closely at a piece of gold, you are seeing the result of two stars that refuse to stay apart. You are seeing the physical manifestation of gravity winning its long war against pressure. The energy required to fuse those atoms is so immense that it can only happen when the laws of normal matter break down entirely. It requires the impossible density we have been drifting through, where a single teaspoon weighs 1 billion tons, and the surface is a crystalline lattice of iron. The gold does not just tell us about the stars, it tells us about our connection to them. We are composed of stardust, yes, but some parts of our world were forged in something far more extreme than a simple star. We carry within our mountains and our minds the remnants of these mergers. The platinum in a medical implant or the gold in a circuit board is a direct link to a moment where two neutron stars became one for one brief second. Before collapsing further into the dark, this realization brings a new kind of humility. It means that the most precious things we value are actually the leftovers of a cosmic disaster. The beauty of the metal is a mask for the violence of its birth. We find peace in the stillness of these objects, forgetting that they were born in a storm of radiation and gravitational waves that could have wiped out entire solar systems had they been too close. As we drift further away from the glow of the kilonova, we begin to wonder if there is a limit to this process. We have seen how two neutron stars can merge to create heavy elements, but we also know that nature has a breaking point. There is a ceiling to how much mass a single object can hold before it can no longer support itself. The pressure of degenerate neutrons is the strongest force resisting gravity in the known universe, but even that strength has an end, and yet there comes a moment when the weight becomes too much, when the scale tips and the star can no longer fight the pull of its own heart. There is a precise mathematical boundary where the laws of physics stop negotiating and start demanding. In the quiet calculations of astrophysics, this threshold is known as the Tolman-Oppenheimer-Volkoff limit. It is the absolute ceiling for the existence of a neutron star, a cosmic weight limit that sits at approximately 2.16 solar masses. For an object to remain a neutron star, it must stay below this number. If you add even a small fraction more mass, a few stray asteroids or a thin stream of gas from a companion star, the entire structure becomes unstable. The stability of these objects depends on something called neutron degeneracy pressure. It is the refusal of neutrons to occupy the same space at the same time, a quantum mechanical pushback that acts as the final line of defense against total collapse. When a star sits comfortably at 1.4 solar masses, this pressure holds gravity at bay with ease. But as the mass climbs toward 2.16, the tension becomes unbearable. The neutrons are squeezed so tightly that they begin to lose their grip on the structure of space itself. Think of it as a ladder of desperation. At one rung, you have the white dwarf, which can hold about 1.4 solar masses before it breaks. One step higher, and you enter the realm of the neutron star, where mass is packed into a sphere only 20 kilometers wide. But at the very top of that ladder, at exactly 2.16 solar masses, the rung snaps. There is no further state of matter to provide support. No force in the known universe can push back hard enough against a weight that exceeds this limit. The difference between a massive neutron star and a black hole is not one of kind, but of degree. A neutron star at 2 solar masses is a physical object with a surface you could theoretically touch, provided you were made of something stronger than any atom in existence. But once the mass crosses that threshold toward 2.17 or 2.2, the surface vanishes. The matter does not just compress, it surrenders, it falls inward, accelerating through its own center, shrinking past the point where light can escape. The transition is an absolute erasure of geometry. One moment you have a city-sized sphere of the densest material in the cosmos. The next, that mass collapses into a singularity, a point of infinite density and zero volume. The event horizon forms not as a wall, but as a mathematical border. While a neutron star bends light around its edges, a black hole swallows it entirely. We can see this tension playing out in binary systems, where two dead stars dance around one another. When they merge, their combined mass often exceeds the Tolman-Oppenheimer-Volkoff limit almost instantly. They create a brief, flickering existence as a hypermassive neutron star, struggling for a few milliseconds to hold itself up against the crushing weight of its own birth. It's a frantic, invisible battle fought at the scale of quantum mechanics and general relativity. But the math is indifferent to the struggle. The limit is hard. Once the combined mass tips past that 2.16 mark, the internal pressure fails. The neutron degeneracy that once held back the weight of a sun simply evaporates under the strain. There is no slow descent. There is only a sudden, violent disappearance from the visible universe as the star falls into itself. This boundary defines the architecture of the dark. It tells us that there is a maximum limit to how much matter can exist in a tangible form before it becomes a hole in the fabric of everything. The universe allows for extreme density, and it allows for impossible gravity, but it does not allow for a neutron star heavier than this specific number. When we look at the remnants of supernovas, we are seeing the survivors of this lottery. Those that fell below the limit became the pulsars we track with our telescopes. Those that exceeded it and became the silent voids that warp the stars behind them. Every black hole began as a failure of matter to support itself. Every neutron star is a victory of quantum pressure over total collapse. The tension remains constant in every corner of space where these remnants drift. A neutron star may spend billions of years in a delicate balance, hovering just beneath the limit, unaware that a single accretion of gas could trigger its end. It is a state of permanent precariousness. The star exists only because it has not yet found enough matter to destroy itself, and so we find ourselves staring at the edge of a cliff. We have traced the journey from a massive living star to a crystalline shell, and from that shell to the crushing weight of 1 billion tons in a single spoon. We have seen how they merge and how they forge the gold we wear on our skin. But every path leads eventually to this same mathematical wall. The universe has a way of cleaning its slate. It takes the most dense objects it can create, and if they grow too greedy for mass, it removes them from the map entirely. The Tolman-Oppenheimer-Volkoff limit is the gatekeeper of the void. It ensures that nothing stays physical forever if it becomes too heavy for space to carry, when gravity finally wins. When we adjust our perspective to see the cosmos not as a collection of objects, but as a map of physical limits, neutron stars cease to be mere remnants and become anchors. They are the points where the laws of nature are stretched until they nearly snap, serving as natural laboratories for physics that no human machine could ever replicate. We usually think of space as an empty void through which light travels in straight lines, but near these objects, the very definition of a straight line dissolves. The mass of a star, compressed into a sphere only 20 kilometers wide, creates a gravitational well so steep that it bends the path of photons themselves. This is not a subtle shift or a slight shimmer in the distance. It is significant gravitational lensing on a scale that defies our intuition. If you were to orbit one of these stars, the gravity would warp the light coming from the surface so severely that you could actually see more than half of the star at once. You would be able to look forward and see the far side of the sphere as the light is dragged around the curvature of space-time, looping back toward your eyes like a mirror made of gravity. The universe is filing each event in space-time itself, and here the file is folded over on itself. The light does not just bend, It curves into arcs and rings, creating a visual distortion where the background stars are smeared into glowing halos around the central white-blue sphere. It is as if the star has placed a heavy weight upon a sheet of glass, cracking the geometry of the vacuum. This curvature tells us that we are no longer dealing with matter in any sense that our bodies can comprehend. We are dealing with a distortion of existence, and yet this warping of light is only one symptom of a deeper instability. The stability we see, the way these stars hold their shape against the crushing weight of two solar masses, is a fragile victory. It is a stalemate between the inward pull of gravity and the outward pressure of neutrons that refuse to occupy the same space. This balance creates an object that is effectively a single atomic nucleus the size of a city, a macroscopic particle floating in the dark. When we map these objects across the galaxy, we realize they are not just dead stars, but markers of extreme thresholds. They mark the boundary between the physical world and the abyss. A black hole is a place where physics stops making sense because the matter has vanished from our reach. But a neutron star is the last place where physics still speaks to us, even if it is screaming. It is the final fortress of tangible matter before the total surrender to the void. We find ourselves drifting through a graveyard of giants, but these graves are active. They pulse, they rotate, and they warp the very light we use to find them. The gravitational lensing serves as a warning that the space around them is no longer hospitable to the laws we learned on Earth. In this region, distance becomes an illusion, and light becomes a curve. But gravity is not the only force operating in this distorted space. There are remnants among these stars that possess a different kind of violence, forces that do not just bend light, but tear at the fundamental structure of atoms. These are the magnetic ghosts among them. Among these collapsed giants, there exists a subspecies of terror that makes the standard pulsar seem dormant. These are the magnetars. While every neutron star possesses a magnetic field, the magnetar is an extremity of nature where magnetism becomes the dominant force of existence. In these objects, the field reaches strengths of up to 10 to the 15th power of Gauss. To find a comparison on our world, we would have to imagine a magnet so powerful that it could wipe the data from every credit card and hard drive on Earth from halfway to the moon. But in the vicinity of a magnetar, this force does not just erase data, it rewrites the laws of chemistry. At 10 to the 15th Gauss, the magnetic field is no longer a passive quality of the star. It is a physical pressure that reshapes the vacuum itself. The atoms surrounding such a star are not spheres. They are crushed into thin, elongated needles, stretched along the magnetic lines, until the electrons are forced into orbits so tight they defy our standard models of atomic structure. If you were to drift toward one, your own body would be dismantled not by gravity alone, but by the magnetism reaching into your cells and pulling the electrons from their nuclei, unraveling your molecular bonds before you even touch the surface. The energy fueling this madness is stored in the star's magnetic field, but it is an unstable treasury. The crust of a magnetar, that rigid, kilometer-thick shell we spoke of, cannot always contain the stress of these shifting fields. When the internal magnetic tension becomes too great, the crust does not simply crack. It ruptures in a cataclysmic event known as a starquake. In a fraction of a second, a massive amount of energy is released in the form of high-energy gamma rays and X-rays. These bursts are so intense that they can be detected by our instruments from across the galaxy. Signals of a city-sized object shivering with such violence that it momentarily outshines entire clusters of stars. The astronomers who first observed these flashes found themselves staring at data that seemed impossible. They saw spikes of radiation that lasted only milliseconds, but carried more energy than our sun produces in days. The team had to reconcile the fact that a tiny invisible point in the dark was capable of such outbursts. It was a realization that the universe does not just contain voids and fire, but also these concentrated knots of magnetic tension, waiting for a single fracture in the crust to scream into the vacuum. But this violence is not eternal. A magnetar is a candle burning at both ends, consuming its own magnetic energy to fuel its outbursts. Over millions of years, the field begins to decay, the intense twisting of the lines slowly relaxes, and the starquakes become less frequent. The blinding flashes fade into a dim rhythmic pulse, and eventually the magnetism that once defined the object as a monster begins to dissolve into the background noise of space. We are witnessing a slow descent into stillness. What began as a supernova explosion, followed by the birth of a magnetic titan, ends in a long, cold silence. The magnetar spends billions of years cooling, its surface temperature dropping from millions of Kelvin down toward the frozen baseline of the cosmos. It becomes a dark ember, a heavy silent sphere that no longer pulses, no longer flashes, and no longer tears at the atoms of passing debris. This is the true life cycle of these remnants. They are born in fire, they live in violence, and they die in an absolute crushing cold. The energy that once warped the vacuum and stretched atoms into needles simply leaks away into the void, leaving behind a mass that is still there, still heavy, but now invisible to everything except the most patient of observers. As we drift further away from these fading beacons, we are left with a haunting realization about the nature of time in the deep cosmos. The universe does not just erase its history, it archives it in these dead stars. Every magnetar that goes dark is a record of a massive star that once existed, a ghost of a collision or a collapse that happened eons ago. They are the heavy anchors of a galaxy that is slowly expanding and cooling, markers of an era when the cosmos was more crowded, more chaotic, and far more violent. We move now past the magnetic ghosts, leaving the screams of the starquakes behind us. We enter the final territories of these objects, where the radiation has stopped and the rotation has slowed to a crawl. The violence has ended, but the mystery remains embedded in the very center of the star. What remains when all energy is spent? The silence that follows these bursts is not a true void, but a heavy expectant tension. Imagine the surface of this star as a frozen ocean of iron, locked in a geometry so rigid it defies every earthly intuition of metal. When the magnetic field shifts, it does not bend, it snaps. The resulting starquake is a fracture in the very foundation of the object, a tectonic shift on a scale that would make a planetary earthquake seem like a whisper. In those milliseconds, the crust ripples with waves of energy that tear through the vacuum, sending shudders through the fabric of space-time itself. We can almost feel the oppressive weight of that magnetic grip. It is a force so absolute that it does not merely pull on matter, it reshapes it. If you were to drift too close, the atoms of your body would no longer be spheres of orbiting electrons. They would be stretched, elongated into thin, fragile needles, aligned with the invisible lines of a field reaching 10 to the 15th power of Gauss. You would become a part of the star's own geometry, a momentary extension of its violent will before being crushed into the crystalline floor. And yet, this is the paradox of the magnetar. It is an object defined by its own instability. The very energy that allows it to scream across the galaxy is the same energy that ensures its eventual erasure. Each flash of gamma radiation is a leak, a small piece of its internal tension escaping into the dark, the star slowly exhaling its power, breathing out the fury of its birth in jagged bursts of light. As we watch this process unfold over eons, the scale of the decay becomes hypnotic. The intervals between the screams grow longer. Centuries pass where the star remains dormant, a silent sentinel in the void, before another fracture occurs, but each subsequent quake is weaker than the last. The magnetic lines, once twisted like tight springs, are slowly unraveling. The tension that once warped the vacuum begins to slacken, and the object loses its grip on the surrounding space. The light fades from a blinding white-blue to a duller hue, then to a ghost of an infrared glow. We see the star transitioning from a predator of the cosmos into a relic. It is no longer the center of a storm, it is the eye of a storm that has finally passed. The violence does not end with a bang, but with a slow, inevitable cooling as the heat of millions of Kelvin bleeds away into the absolute zero of the intergalactic medium. The star becomes a heavy secret, hidden in plain sight. It still possesses the mass of 2 suns. It still curves the path of every photon that passes near its edge, but it no longer announces itself to the universe. It has become a dark anchor, a point of infinite density and zero noise. We are left to wonder how many billions of these silent spheres drift through our own galaxy, invisible ghosts of ancient supernovas holding their breath in the cold. We have traveled from the blinding surface of these titans down through their crystalline crusts, but we are now approaching a boundary where our current maps of physics simply fade into white noise. At the very center of a neutron star lies a region so extreme that it ceases to be matter as we define it in any earthly laboratory. Here, the internal pressure is not merely immense, it is absolute. It is a force that does not just crush atoms, but erases them. In the heart of this city-sized sphere, the gravity is so relentless that it forces protons and electrons to merge, compressing them into neutrons through a process of sheer, violent necessity. The very identity of the particle is stripped away, leaving behind a dense sea of neutral matter that defies every intuition we have about how solids or liquids behave. And yet, as we drift deeper toward that central point, even the neutron may not be enough to withstand the weight. There is a quiet, persistent debate among those who study these objects about what happens when the pressure exceeds even the limits of neutron degeneracy. Some models suggest that the neutrons themselves might dissolve, breaking apart into their constituent parts, a primordial soup of quarks and gluons. This state of matter, known as quark-gluon plasma, is believed to have filled the entire universe for a fraction of a second after the Big Bang, but now it may only exist in these hidden cores, locked away beneath kilometers of nuclear crust. What does a star look like when its heart has turned into a fluid of subatomic fragments? We cannot see it. No telescope can pierce through the layers of degenerate matter to photograph the core. We are forced to rely on the subtle ripples of gravitational waves and the precise timing of pulsar beams to guess at the density of the center. The scientific community remains divided, with different teams proposing varied equations for how this inner core is structured. Some believe it is a superfluid that flows without friction. Others suspect a crystalline phase of quarks that creates a rigid, exotic interior. The mystery persists because we cannot recreate these pressures on Earth. We can smash atoms together in massive colliders to glimpse the quark-gluon plasma for a trillionth of a second, but a neutron star holds that state in a permanent crushing embrace. Every single one of these stars is a natural laboratory conducting an experiment in high-density physics that we are only beginning to observe from a distance. Future measurements, perhaps from next-generation gravitational wave detectors or more precise X-ray timing missions, may finally reveal if the core is a smooth ocean of quarks or something even more strange. We are left staring into a darkness that refuses to give up its secrets. The center of the star is the final frontier of matter, a place where the laws of chemistry and atomic structure are replaced by the raw, unfiltered mathematics of general relativity and quantum chromodynamics. It is a region of the universe where solid has no meaning, and density becomes a word that can no longer describe the reality of what is there. As we slowly pull away from this impossible core, leaving the crushing pressure behind, the noise of the physics begins to fade. The violent collisions, the screaming magnetic fields, and the dissolving atoms, all recede into the distance. We drift back out through the crust, past the frozen surface, and leave the star as a small, dim point of light in the vastness. Around it, there is nothing but the cold reach of the interstellar medium, the silence of the void. It is a strange and humbling realization that we exist at all. We are biological entities made of soft tissues, fragile membranes, and salt water, living on a world where gravity is a gentle pull rather than a crushing force. For us, the idea of stability is a quiet house or a steady heartbeat. But in the deep reaches of the cosmos, stability takes a form that defies every human intuition about what it means to be solid. Within the heart of a neutron-star, the only thing preventing total collapse into a black hole is a phenomenon known as neutron degeneracy pressure. It is not a physical wall or a chemical bond, but a fundamental law of quantum mechanics. The universe forbids two neutrons from occupying the same state at the same time. When gravity tries to squeeze these particles even tighter, they push back with a desperation that creates one of the most rigid structures in existence. This degeneracy pressure is the only reason these stars do not vanish into singularities. It is a silent, invisible war between the crushing weight of two suns and the stubbornness of subatomic particles refusing to be erased. We spend our lives fearing the violence of the world, a storm, an earthquake, a sudden crash, yet we are floating in a universe where entire solar systems can be shredded by the tidal forces of a city-sized remnant. We live in a reality where magnetic fields can dissolve atoms and where matter is compressed until it becomes a superfluid that flows without friction. The scale of this violence is so absolute that it ceases to feel like destruction and begins to look like a different kind of order. There is a profound irony in the fact that the very elements that make our bodies possible were forged in these crucibles of extremity. We are composed of atoms that require the death of massive stars and the collision of impossible densities to exist. The calcium in your bones, the iron in your blood, the gold in a wedding ring, these things are the shrapnel of cosmic catastrophes. Our existence is not an accident occurring despite the violence of the universe, but a direct result of it. We are the ghosts of dead stars reorganized into consciousness. We are small, not just in size, but in our fragility. A single breath of air on the surface of a neutron star would be crushed into a layer thinner than a single cell before the brain could even register the sensation of touch. Our entire history, every empire that rose and fell, every war fought, and every love known, happens in the narrow, quiet margins where gravity is weak enough to allow liquid water and soft skin. We inhabit the gaps between the monsters, and yet there is a miracle in this disparity. The fact that we can stand on a cooling rock in a suburban neighborhood and use mathematics to map the interior of a star 20,000 light-years away is an act of defiance. We are fragile things, but our minds have grown large enough to hold the image of neutron degeneracy pressure. We can perceive the weight of 1 billion tons in a teaspoon. We can hear the rhythmic ticking of a pulsar across the void. The universe does not care that we are soft, yet it has allowed us to become its witnesses. We drift through a cosmos that is mostly emptiness, punctuated by the points of unimaginable intensity. For every neutron star screaming into the dark, there are billions of light-years of silence. We have spent this journey descending into the most extreme environments known to physics, moving from the crystalline crusts to the crushing depths of the core, feeling the pull of gravity that bends light itself. We have seen what happens when matter is pushed past its breaking point and found a terrifying beauty in the result. But as we move further away from those violent remnants, the tension begins to dissolve. The heavy mathematics of general relativity fade into the background. The crushing pressure of the degenerate core no longer reaches us. The screaming magnetic fields are now just distant whispers in the radio spectrum. We are returning to the scale where we belong, the scale of breath and sleep and silence. The violence is still there, occurring 1,000,000 times over in every corner of the observable universe, but it is far away. It is a storm happening on another continent of space-time. Here, in the quiet of your room, the gravity is soft. The air is still. Your heart beats in a rhythm that does not need to compete with the spin of a pulsar. The weight of the cosmos is no longer yours to carry. You can let go of the numbers and the scales. You can leave the impossible densities behind. As we drift back into the velvet dark, there is nothing left to measure and nowhere left to fall. There is only the slow, steady pull of rest. The universe is a patient sculptor, carving beauty out of absolute destruction. Somewhere in the deep velvet of the void, old neutron stars have spent billions of years cooling, their initial fire fading into a silent, frozen equilibrium. They are the quiet ghosts of giants drifting through an eternity where time itself seems to slow down. We are small and we are fragile, yet we possess the singular ability to look upon these impossible weights and feel a sense of peace. Let the scale settle. Let the weight dissolve into the dark. Let us be the generation that was humble enough to listen to the silence. Thank you. Sleep well tonight.